In the previous video, we wrote down the definition of a Fourier series for a 2-pi periodic function f of x. What I'd like to do now is use that definition to find the Fourier series for the function I've graphed here. This is a piecewise function defined to be equal to minus pi over 2 when x is greater than or equal to pi and less than 0. And then when x is greater than or equal to 0 but less than pi, it's defined to be pi over 2. The extension I've graphed here, so notice that I've graphed it from minus pi to pi, but I've gone past that, and that comes from the fact that we're told that this function is 2-pi periodic. So giving us the information about this function on an interval of length 2-pi, plus the information that it's 2-pi periodic, allows me to have a complete picture of what that function actually looks like. Because recall that we've defined this to mean that f of x plus 2-pi is equal to f of x for all x. And that means that I could then find f of any other x value by being able to relate it back to one of the ones between minus pi and pi. So I will say in my computation, the graph isn't terribly important, but I'm going to point out a little bit later some features of f of x that, if observed, might actually simplify the process of finding the Fourier series. Consequently, I strongly encourage you to sketch out the graph anytime you're asked to find a Fourier series. So at this point, what I'm thinking of is I need to find the general formula. So I know I'm looking for something in my final answer of the form of our definition. And I should start that at 1. So what I need to do is to figure out what a sub 0 is, and a sub k and b sub k for this particular function. So that's the goal here. And that's where the other part of the definition comes in. We defined these in terms of integrals. In particular, we said that a sub 0 would be 1 over 2 pi, the integral from minus pi to pi of the function f of x. So in this particular example, we have our piecewise definition of f of x. So note that I can split this up. To integrate f from minus pi to pi, what I really need to do is from minus pi to 0, replace f of x with negative pi over 2, and then add that to the integral from 0 to pi of positive pi over 2. This is due to the piecewise nature of f of x. And I want to be careful here that I distribute that 1 over 2 pi throughout. So here I have negative pi over 2 times the length of my interval, which is pi. This is just a constant integrand. And likewise, positive pi over 2 times the length of my interval. And these are going to cancel out, and I'll get 0. So I want to remember that my a sub 0 is going to be 0. A sub k we defined as 1 over pi, the integral from minus pi to pi, of f of x times cosine of kx. Much like I did above, because f is piecewise defined, I'm going to write this as 1 over pi, and then from minus pi to 0, I'll integrate minus pi over 2 times cosine kx. And from 0 to pi, I'll take the integral of positive pi over 2 cosine kx. So what we can think of here is that I have my 1 over pi. I want to find my antiderivatives. Well, in this case, maybe to make this a little bit easier, let's factor the pi over 2 out front. So I have a pi over 2. And now I'm just focusing on, in the first integral, I still have the negative, so I'm going to anti-differentiate negative cosine of kx. So the antiderivative of negative cosine is going to be negative sine, but we have to be a little bit careful with the kx. So if I were going to be very formal here, I could think about the fact that u is kx, du is k dx, so 1 over k du is equivalent to dx. So if I were going to integrate cosine kx, it's going to be 1 over k, the integral of cosine of u. And so when I anti-differentiate, I will bring that 1 over k with it, and this will be sine of u, or kx. So every time from here on out that I'm going to anti-differentiate cosine of kx, what I need to remember is that that brings with it a 1 over k. So formally that's from u substitution, but we don't need to do that every time. This one, because I have the minus, this is going to be minus 1 over k sine kx from that work in orange. I'm evaluating this part from minus pi to 0, and then I'm going to add that to the antiderivative of positive cosine kx, which is 1 over k, sine kx. And that part is evaluated from x equals 0 to x equals pi. So we can cancel these pi's, and now I can see that what I'm left with is bringing the 1 over k out front. I have 1 over 2k, and then I'm going to have minus sine of 0 minus a negative, so plus sine of minus k pi plus sine of k pi minus sine of 0. So recall that sine of 0 is just 0. That's something we can cancel out right away. And then think about what we have here. So sine of minus k pi and sine of k pi. Remember that k is representing 1, 2, 3, etc. So this is a whole number multiple of pi that we're evaluating sine at. And sine evaluates to 0 at pi, at 2 pi, 3 pi, etc., negative pi, negative 2 pi, negative 3 pi, etc. So these actually also equal 0. And that's going to be something that we'll want to remember when we're evaluating Fourier series. This comes up a lot, that you encounter sine of plus or minus k times pi, and that's always going to be 0 because k is a whole number here. Consequently, what we're finding is that a sub k is 0 for all k as well. This might seem a little disconcerting, but we're going to see that b sub k is not 0. Of course, if it was, this would be a very bad approximation. So let's finally find b sub k, and notice that that's going to be a very similar looking integral to the one we did above. The only difference is that we replace cosine with sine kx here. So much like I did above, because of the piecewise nature of f of x, we split this up as an integral from minus pi to 0, in which case f of x is negative pi over 2, and then add that to an integral from 0 to pi, in which case f of x is positive pi over 2. And do some similar things from before. Again, I'm going to factor out my pi over 2 that's common to both integrands. And then the antiderivative now is of negative sine kx. So here, the antiderivative of negative sine is positive cosine. And for the very same reasoning that I did with in orange up there, every time I anti-differentiate sine of kx, I need to bring out a 1 over k. This is evaluated from minus pi to 0. And then the antiderivative of positive sine is actually now negative cosine kx. And again, I'm going to bring out a 1 over k, evaluating this from 0 to positive pi. We can cancel the pi's. I can factor out the 1 over k so that I have 1 over 2k. And then let's evaluate what we have left. So I'm going to have here a cosine of 0 minus cosine of negative k pi. And then we're going to subtract cosine of positive k pi minus cosine of 0. So we'd like to simplify this. I don't want to put this in place of my b sub k coefficient, and we can simplify this. For one, keep in mind that cosine of 0 is 1. So right away, one thing I can do is recognize that I have a positive cosine of 0 minus a negative, so plus another one. So I have a 2 in here, positive 2. We're subtracting cosine of minus k pi, and we're subtracting cosine of k pi. The other observation that's going to help me here is to recognize that these are actually the same. Cosine of minus k pi is equal to cosine of k pi. The reason is cosine of x is an even function. Recall that that's one of our definitions, that if you evaluate an even function at a positive x value and the same x value but negative, they should equal the same value. So this doesn't mean that they cancel out because they're both being subtracted, but it does mean that I can write this a little bit more succinctly if I just replace this cosine of minus k pi with cosine of k pi. So I could express this as just subtracting 2 times cosine of k pi. So it makes it a little bit easier to think about what's happening here. So notice that now I can see that I can cancel the 2's. So I at least have knocked this down to this. So there's something important to keep in mind here, that cosine of k pi, we have actually seen this in a series before, that takes on one of two values. So if I really want to think of the different possibilities here, if you consider k and then cosine of k pi, if we just consider a little chart of this, so when k is 1, cosine of 1 pi is minus 1. When k is 2, cosine of 2 pi is positive 1. Cosine of 3 pi is negative 1. Cosine of 4 pi is positive 1. So what we can think about here is that that means that the part in parentheses is going to take on one of two values. So at this point, b sub k, we said is 1 over k times the quantity 1 minus cosine of k pi. What this evaluates to depends on whether or not k is even or odd. So if k is even, then cosine of k pi is positive 1. So subtracting it from 1, we get 0. But if k is odd, cosine of k pi is negative 1. So in parentheses, we would have 1 minus a negative 1, or 2. And so in those instances, my b sub k would be 2 over k. So now we've done all of the work finding our coefficients. I'm ready to plug them back in. What's going to happen here is we're going to see that in this instance, there is no a sub 0 because it was 0, and every a sub k was 0. So if that happens, that means that our Fourier series will be reduced to just a sum of the sine terms. But the only thing we have to be cautious with, and we've had to do this with Taylor series before, is every other sine term has coefficient 0. And that means that we have to take special care when expressing this in sigma notation. So the Fourier series, we know, is only of the form b sub k sine k. So it's going to be b sub 1 times sine of 1x plus b sub 2 sine of 2x plus b sub 3 sine of 3x plus b sub 4 sine of 4x, etc. And in this instance, we know that the b sub 2 is 0 and b sub 4 is 0, and so on. Plugging in the pattern, for b sub 1, we should get 2 over 1. And this is sine of 1x that it sits in front of. Then the next term is going to be our next odd value, in which case we get 2 over 3, and this would be sine of 3x. And then I could imagine the next term would be 2 over 5, sine of 5x. So my purpose in writing these out is only to help me to see the pattern that I should get and how I should express this in sigma notation. We can take advantage of some of what we learned with Taylor series when we had to find a pattern. So what I'm going to observe here is I'm trying to write the sum of the b sub k's, where k ranges from 1 to infinity, but I want to write it in a way so that it skips over even k values. We've seen before that you could express, instead of k, you could put 2k plus 1. The only difference is, because my index starts at 1 here, if I want to make sure that the first k value is actually 1, instead of 2k plus 1, I want to put in a 2k minus 1. So when we had indices that started at k equals 0, we put in 2k plus 1. That's the only kind of subtlety. But beyond this, notice every term has a 2 in the numerator, and then whatever was in the denominator was also multiplied by x in the sine function. Those had to match. So if I want to now, I don't want to put in k because that would provide me with non-zero even indexed values. So here's where I put in 2k minus 1 in both of these spots. And notice that the 2k minus 1, that hits 1, 3, 5, etc. So this is, in fact, my final answer for my Fourier series, and I've expressed it in summation form.